All right, welcome to the 2019 FRQs. We're going to start with FRQ number 4. So just as a reminder, FRQs numbers 1 and 2 are calculator active, but 3 through 6 are not calculator active. So when you're practicing these, make sure you are not using a calculator. You will be giving yourself a false sense of security that you won't really have on the actual exam. All right, so reading through number 4, we have a cylindrical barrel with a diameter of 2 feet, collects collected rainwater as shown in the figure above. The water drains out through a valve that's not shown at the bottom of the barrel. The rate of change of the height of the water in the barrel with respect to time t is modeled by the differential equation dH over dt is equal to the negative 1/10 times the square root of h. H is measured in feet. T is measured in seconds. And then they do give us the formula for the volume of a cylinder, which you probably already know. All right, part A. Find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet and indicate units of measure. All right, so in starting this one, this is a related rate problem. And what I'm going to do is I'm going to actually go through the given information one more time and notice, kind of just write down all of the information, and then I'll jump into part A. So the diameter of this barrel is 2 feet. Now, the diameter is unchanging here. The radius is 1. And throughout the entire problem, these are never going to need to be represented as variables because these are unchanging amounts. This barrel is not changing its diameter at all. Now, the height, however, is changing. And so they're telling us the rate at which it's changing is negative 1/10 times the square root of h. And h is measured in feet. All right, for part A, we want to find the rate of change of the volume. So what we are trying to find is dV over dt. And what we also know is that the height of the water is 4 feet at the moment where we want to find the rate of change of the volume. And then they did tell us the formula for the volume of a cylinder, which was kind of them, which is pi r squared height. Now I'm going to be finding the rate of change of this, so I'm going to be taking a derivative implicitly with respect to time. Notice time is not one of the variables in the equation. You might also want to notice that r, remember, is unchanging. So because r does not change, we actually can replace r with 1. You should only do this if a variable is truly unchanging throughout the entire context of the problem. And in this instance, it is. The diameter and thus the radius of the barrel will not ever change in this problem. So I am actually going to rewrite this volume formula as a more simple formula as pi times h. So then if I take the derivative of this, the derivative of pi h is pi times the derivative of whatever h is. And I want to now evaluate this specifically when the water is at a height of 4 feet. So I will evaluate this. Now remember, dH over dt, they gave us, but I want h to be 4. So since the square root of 4 is 2, I could get negative 2/10. I could choose to reduce that or not. So if you wrote negative 2/10 pi instead of negative 1/5 pi, that would be fine. But it's a good idea to always go back before you decide you're done with the problem and just double check. And you might notice on this one it says we need to indicate the units of measure. We need to indicate the units of measure. So if we left off the units of measure, we could not get full points on this problem. We were told that the height was in feet. And since we're in volume, that would be feet cubed. But this is a rate of change, so we always want to compare this to time, and time is measured in seconds. And it is common for students to leave off the volume. I'm just going to compare this quickly with the scoring guideline. So if I look at the scoring guideline, this part is worth 2 points. The first point comes from recognizing, getting to this point where somewhere we have dV over dt equals pi times dH over dt. Now, if you replace dH over dt right away with negative 1/10 root h, that's fine. You would still get that. So that could be in a variety of forms, but we need that. And then notice that the answer point must have units. So if we did not have the units, we would only get 1 out of 2, even though we had the correct value of the answer. But we have that correct expression for the rate of change of the volume, and we have the correct answer with units. So we would get 2 out of 2 points for part A. All right, part B. Specifically at the moment when the height is at 3 feet this time, is the rate of change of the height, which is dH over dt, with respect to time, increasing or decreasing? Now, students answer the wrong question here on this one. What students tend to do is many times students recognize, hey, this is actually looking at, we need to know the sign of some type of derivative to answer this question, but they often look at the sign of the first derivative. But the increasing and decreasing, this right here, that's more derivative language. So when you see that, you're taking the derivative of whatever they're asking about. So this is really asking us to look for the sign of the second derivative. That's really what we're looking at here. Is the second derivative positive or negative? That's really what we're looking at. Okay, that's what we really want it to do in order to solve this problem. So if I start with my first derivative and I take its derivative, keep in mind that you should not substitute in the 3 for h until after you've taken the derivative, because the height's changing. So something that's changing cannot be substituted in until after you've done your derivative. So if I wanted, maybe I'll rewrite this as h to the power of 1/2. So then the second derivative here, I'm going to use the power rule. So I would get, h to the power of positive 1/2, my apologies. So I would get negative 1/20th, h to the negative 1/2. And then because this is being done implicitly with respect to time, which is not our input variable in the expression, I do need to write times dH over dt. And now I'm going to evaluate this specifically when h is equal to 3. And so I would have negative 1/20th over the square root of 3 because of that negative power for h. Now dH over dt, remember, was negative 1/10 times the square root of h, which in this case is 3. Now looking at this, I can tell this is going to be a positive answer. Now I can actually get that answer if I want. The root 3's will cancel out and I'll get 1 over 200 as my rate of change here. Let me see. Again, just it wants me to explain their reasoning. So I'm going to say that dH over dt is increasing because the second derivative of that expression is greater than 0. This is my justification. However, I also, I also do need the work to support my conclusion here. All right, let's take a look at the scoring guideline to see how we did on this one. Maybe if I can find it. Oops. All right. So we, the first point is going to come from knowing that we need to take the second derivative. And notice this isn't the entire second derivative. If you forget the dH over dt, you're still going to get the first point. Now to get the second point, you have to recognize that we're doing this implicitly. The third point is going to come from the explanation, noticing that it's a positive value for the second derivative, and therefore the rate of change of the height is increasing. So we would have gotten 3 out of 3 here. Now they also, you might have noticed, also mentioned, sorry, I'm having a little tech difficulties. You may have also noticed that they also mentioned that the height was going to be positive to kind of also verify that this would be a positive answer, but you can see that in my work. So I don't actually have to put that in there again. All right, part C. At time is equal to 0, the height is 5 feet. So the height at time 0 will equal 5. I have an ordered pair there. I'm going to use separation of variables to find an expression for h. Well, this was a nice little hint. They sometimes don't give you that hint. So that was nice that they did this. I need to go back and find a differential equation that has dH over dt in it. This is what I'm starting with. I'm going to need to separate those variables and integrate in order to find the solution here for h. And because I have an ordered pair, this will be the particular solution. All right, so what I'm going to do is I'm going to go ahead. The numerator here should stay on the left side. We want both of this, the DH and the DT, we want them to both be numerators. We do not ever want them to be denominators. So I'm going to multiply both sides by DT in order to move the DT over. I keep the constant multipliers over on the right-hand side, and then this root H needs to be over on the left-hand side. I'm going to divide by root H in order to move it over to the left-hand side. A little trouble with writing, I guess, today. Here we go. Now I'm going to integrate both sides in order to work on finding the solution. Now, if you want, you could rewrite this. It might be more helpful to rewrite this as h to the power of -1/2. This, by the way, is not a natural log, okay? If we have 1 over h to the power of 1, even if we have things added, even if we have things multiplied, that would be a natural log, all right? But if you have a different power of your variable, of your input variable here, that's not a natural log, this is power rule. So that's why I rewrote it in this form. So I'm going to add 1 to the power and divide by that power, or multiply by the reciprocal. And then over here, this would be -1/10 t plus c. So if I divide everything by 2, then the square root of h, which for me is a little easier to interpret, would be -1/20 t plus c. When you divide a constant by 2, you just get another constant. Now you can choose when you substitute in this ordered pair. I like to substitute it in right now before I square everything. For me, it just seems easier. So from right here at this step, I'm going to substitute in the fact that when t is 0, h is 5. So this would be the square root of 5. T would 0 out is equal to my constant c. Now, since I did it from this step, when I rewrite this, I'm going to make sure that I put that root 5 back in that step and not in a different step. And as a last step, I do need to isolate h. I'm going to square both sides. Do not simplify this. You'll probably simplify it wrong. Many students do. If you cannot distribute that power because of the addition here. Okay, addition and subtraction, you can't distribute that power. You'd have to expand this out, like think of like FOIL or something like that. So my answer here for h is -1/20 t plus root 5 quantity squared. All right, let's see how we did. And again, I got things moving on me. I'm not sure why, sorry. All right, I have the right final answer, but let's just see how I did on the points. Okay, I did separate out the variables as they did here. Okay, my antiderivatives were correct. You get 1 point for each side. At least one of those has to be correct in order for them to continue grading. If both of those are incorrect, they will stop grading. The third point is going to come from the fact that you have the plus c and you plugged in the ordered pair 0, 5 somewhere. Now they plugged it in a different place than I did. You might remember the constant I got was root 5. They got 2 root 5. That's because they substituted in earlier than I did. But notice the final answer is the same. And then the final point, fourth point, comes from isolating h. So you can't leave it to root h. You must isolate it. If you do not separate the variables, you will not get any points. And if you don't have the constant of integration, you don't write plus c, then unfortunately, the most you can get is 2 out of 4 points. But we did those things, and so we will get, for this one, all 4 points. So that's how you get a 9 out of 9 on this FRQ. All right, so on to FRQ number 5. Again, this is non-calculator active. So R, this is like chapter 8, part 2, all in one question. R is the region enclosed by the graph of G and H. The y-axis and the vertical line x equals 2 as shown. Let's figure out which of these is G and which is H. I'm a little bit more familiar probably with quadratics than most shapes, and so I want a quadratic. Notice this at 1 here, x equals 1 is going to be where my vertex is, and it's opening down. So this almost looked like a quadratic, but notice it dips back up again. So this must be H, and this is G. All right, so for part A, we want to find the area of R. Now, area is just either if it's dx, if we have vertical slices, that's top minus bottom. If it's horizontal slices, it's right minus left. But if I connect these, one is always above the other. So I'm going to be using vertical slices, so I'll be using dx. So as I write this for part A, I'm going to be doing the definite integral. My region goes from 0 to 2 along the x-axis. And I want to do top minus bottom. So I'm going to do h minus g. And then all of this is dx. All right, so that's my plan. Now I've got to actually, they do want me to find it. No calculators allowed. So I do have some computation here that I need to do first of all. So remember, x minus 1 quantity squared really does mean that binomials times itself. And if you expand that out, and then I would need to distribute, this would be 6 minus 2x squared plus 4x, watch your signs, minus 2. If I distribute this negative here because I'm subtracting all of g, I get plus 2. Those will cancel out. Minus 3 times the cosine of pi over 2x dx. And I'm just going to check to see if this can simplify, and I'm going to work on integrating it. Now, depending on your comfort level of doing some u substitution in your head, if you're really confident doing u substitution in your head, there's no need for you to split these integrals. But if you do struggle with u substitution, if you want, and you really need to write it all out, you might want to split these up into 2 different integrals. It's totally up to you as to whether or not you do that. It's definitely not required. Okay, you can undo the chain rule of pi over 2x for just this term by multiplying by that reciprocal of 2 over pi, if you're comfortable with that. But if you need to split it, then you can. So I'm going to just use power rule here on the left. I'd get 6x minus 2/3 x cubed plus 2x squared, and that's going to get evaluated at 2 at 0. Minus, and again, if you need to use u substitution, u here would be pi over 2 times x. So du would be pi over 2 dx. I have the dx, but not the pi over 2. So I'll go ahead and multiply both sides by that reciprocal in order to isolate dx. So dx is going to be replaced by 2 over pi. Now it's going to multiply this negative 3, so that'll be negative 6 over pi. And then if you want, you can change these limits right here, just one option of many. If I do that, this would now become pi and 0, and this would be the cosine of u du. Now, if you change the limits, then you are never leaving that u. You're staying there. If I evaluate this at 2, I'd get 12 minus 16/3 plus 8, and then minus 0 for all of that part. And then over here, minus the integral of cosine is sine. So this would be minus 6 over pi sine of u, which will get evaluated at pi and 0. By the way, on the real FRQs, you have plenty of room. So if I simplify this, this is 20 over 3 minus 16 over 3. Oh, not 20 over 3. How about just 20? I guess if I write that with a denominator of 3, that'd be 60 over 3. So this part over here would become 44 over 3 minus 6 over pi times the sine of pi minus the sine of 0. Well, the sine of pi is 0. The sine of 0 is 0. This whole last part zeroes out, and I get 44 over 3 for part A. So that one was very, heavy on process for your integration, computation, all of that. And let's see how we did. We got the right answer, so that was good. This is out of 4 points. Our integral is correct. The antiderivative specifically of this is listed. Now, they wrote it this way in terms of x. We wrote it in terms of u in an equivalent form, so ours would get the point. The antiderivative of everything else gives you another point. So if you had a really hard time doing the derivative of the cosine part, but you did all of the polynomial parts correctly, then you could actually go ahead and still get that third point, even if you didn't get the second. The answer you're not going to be able to get if you don't get both of those other ones. Now, you could have gotten that answer point from here as well. You do not actually have to combine to the 44 over 3. So that's up to you how you want to do that. And you could have had a different combination of numbers in here depending on the process you use to integrate this. So we got 4 out of 4 for that one. All right, let's try part B. B, region R is the base of a solid. Okay, so this looks like this is going to be cross sections. Notice, so this is where we do the volume with known cross sections. Okay, let's see what we've got. At each x, the cross section perpendicular to the x-axis. This is telling us that this is going to be dx. Has this area. So this is interesting. It's not a square. You know, a lot of times in these we might do like, oh, however we do this, we would do the integral of whatever the formula is for the area. A lot of times that's a square, or that's going to be a triangle or whatever. Well, this one is interesting in that they already told you the formula for that area. So it's some whatever shape it is, and that's the formula for its area. We want to do this on the interval from 0 to 2. Well, 1 over x to the power of 1 is natural log. If it's just got a term added and subtracted to it, it's just the absolute, or the natural log of the absolute value of that. Now, if there is like a 2x or a multiplier here, then you are going to need to think about u substitution. But with addition and subtraction, you don't have to. And this is evaluated at 2 and 0. So this would be the natural log of the absolute value of 5 minus the natural log of the absolute value of 3. But 5 is already positive. There's no need for us to actually leave that absolute value here. Same thing here with the 3. Now, would they mark you down for it? I don't know. It just seems a little unnecessary. I think it's something you would be expected to do. You could leave your answer like this. There's no reason to condense this. However, if you wanted to, this would be another acceptable answer that could be written. Part C, write, but do not evaluate. Yay! That's great news. Oh, I guess we should compare. Let's see how we did on B. Okay, worth 2 points. The first point comes from the correct integral, which we had. The second comes from the final answer, which we had. And remember, you can have that in equivalent form. So we got 2 out of 2 points there. All right, let's do C. Write, but do not evaluate an integral expression that gives the volume of the solid. All right, so volume generated when R is rotated. Okay, so we are going to be using either a disk or a washer method here. And specifically, we're rotating this along the horizontal line where y is equal to 6. Remember, this was H, this was G. The line, horizontal line y equals 6 is right here. Because there is some white space in between my axis of revolution and the shaded region, I will be using the washer method here. And if you think about drawing your radii, that can help a little bit. All right, so washer method, pi times the big radius squared minus the small radius squared. I do need to decide if this is going to be dy or dx, and that will help me fill in the rest of this. To make that decision, I'm going to connect each boundary to the axis of revolution. So the top boundary and the bottom boundary. Notice that those are vertical slices. That tells us this will be dx, which means these interval numbers need to be x numbers, and this goes from 0 to 2. Within each of these, since we're doing this dx, you're going to be doing top minus bottom for each of these radii. Each time, top minus bottom. So for the first radius, I need the bigger one, the one that is longer. Top minus bottom would be 6 minus g of x. And then for the smaller radius, top minus bottom would be 6 minus h of x. If you'd like to put in the expression, you can, but I think it's going to save you some time to not do that and reduce potential careless errors. All right, let's compare. All right, we need the correct limits. They're giving us 1 point for just having that pi and the correct limits. Then we need the form of the integram, meaning washer, basically. Okay, all of this. And then the last points, having the entire integram correct, including your radii. Needs to be in that order. 6 minus g is a bigger radius than 6 minus h, so it has to be written in that order. So we did it. We got all 3 of those points. Okay, so that was a 9 out of 9 on. All right, we're on number 6 now, which is probably the one that I think is the most challenging out of the 3 that we're looking at today. Again, this is non-calculator active. We've got 3 functions, f, g, and h. They are twice differentiable. Now, almost always when they tell me that, I usually start off by mentioning somewhere that they are thus continuous. If you want, you can do that right at the beginning of the problem. That's totally up to you, but it's not a bad idea. But F, G, and H are differentiable and thus continuous. That often is a wise idea. Not that you totally have to do that at that point, but if you do that at the beginning of the problem when you see that, then if you need it for a theorem, it's done. So it's not a bad idea to just kind of get in the habit of doing that. All right, for part A, we want to find h prime of 2. Oh, I didn't finish reading this. G of 2 is equal to the same thing as h of 2. They both have the ordered pair 2, 4. And we also have this line here, and it's tangent to both of them at x equals 2. So however these curves look, they meet when x is 2 at the point 2, 4. And then we have this tangent line, which the way the tangent line is probably tells me it looks something like that. But then we have this tangent line here that's the same tangent line for both of them. That right there, that's the tangent line. Okay, if we want to find, and that's for both G and H, and we want to find h prime of 2. Well, another way to say h prime of 2, if it's a derivative, this is the slope of the tangent line at x equals 2. Well, we have the equation for the slope of a tangent line, and the number in the slope position is 2/3. So we're done with that one. Okay, so A is done. All right, let's take a look at B. A is another function given by 3x cubed times h of x. We want to find an expression for a prime of x, and then we also want to find a prime of 2. Oh, I guess we'll check at the end. All right, so for part B, a of x is 3x cubed times h of x. So first we want to find a prime of x. So I'm going to use the product rule. I intentionally drew this here just to help me recognize the product rule. So I'll do the first times the derivative of the second plus the second times the derivative of the first. So there's my expression for a prime of x. I also want to find a prime of 2. So let me just rewrite this. This would be, let's see, 2 cubed is 8 times 3 is 24. Nice. Times h prime of 2 plus h of 2 times, let's see, I think I didn't do my derivative somewhere. Let's try this part again. This would be 9x squared. The second times the derivative of the first. I was like, wait a minute, these shouldn't be the same. All right, now that that's fixed, if I substitute in a 2, I'll get a 36. I do need to simplify this. I cannot leave this function notation in here. So h prime of 2 we actually found in part A. That's 2/3. So this is 24 times 2/3 plus h of 2 they gave us at the beginning of the problem times 36. Now you could leave that answer. In fact, you should. If I were doing this problem, I would leave that answer. They probably on the scoring guideline simplified it just because they tend to on the scoring guideline, but this would be 16 plus 144, which is 160. But you will get 4 full points if you get to this or some equivalent version of that. All right, part C. The function h satisfies this equation. All right, so now we have this equation for h, but it's kind of interesting because it has f as part of its equation for everything except not at 2. So that's an interesting thing for them to say that. It is known, however, that the limit as x approaches 2 of h can be evaluated using L'Hopital's rule. So that tells me that if I substitute in a 2 here, I would get an indeterminate form. I'm going to use the limit as x approaches 2 of h to find f of 2 and f prime of 2 and show the work that leads to your answer. Okay, there's a lot of stuff on this one, so let's see if we can break this down. I'm actually maybe going to kind of review this idea again that these are all continuous functions, f, g, and h. We're not dealing with g on this one, but we're dealing with f and h. So for part C, I'm going to recognize here that because these are continuous, the limit for each one of these, they're continuous specifically at 2. All right, but at all of them. The limit as x approaches 2 of f of x should equal f of 2. That's from our limit definition, or that's from our definition of continuity. The limit from the left has to equal the limit from the right, which would be this. It has to equal the value of the function at that same input. Well, that's also true for h, by the way. The limit as x approaches 2 of h of x has to equal h of 2. This is going to come into play in this problem. Okay, now remember, we know what h of 2 is. H of 2 is 4. So we know that this whole limit has to equal 4. But we also know it's going to be evaluated during L'Hopital's rule. Now, when I do L'Hopital's rule, what you should do, especially if you know L'Hopital's rule is going to be used, is first we need to justify, examine the limit of the numerator separately from the limit of the denominator. Let's just take a look at the limit of the numerator. The limit as x approaches 2 of x squared minus 4, if I use substitution, would be 4 minus 4, which is 0. Now, since they told me that the limit of this whole expression for h will be used during L'Hopital's rule, I need to get it in indeterminate form. And since I need an indeterminate form, what I would then know, is that the limit as x approaches 2 of the denominator, which is 1 minus f of x, quantity cubed, must also equal 0 because I need an indeterminate form in order to make this eligible for L'Hopital's rule. Well, I can then solve this. What this means is that if I substitute in a 2 for this expression for x, I should be able to get a 0. I'm going to cube root both sides. And then when I solve this, f of 2 must equal 1. That was one of the things that they told me I had to do. Now, I also need to find out what f prime of 2 is. And now I'm going to work more kind of with this whole continuity idea a little bit more. I know that the limit of h has to equal 4. That's not going to happen initially with substitution because I would get 0 over 0, which is an indeterminate form. But if I use L'Hopital's rule, I should be able to get that form. So I'm going to be working with L'Hopital's rule now for h. So because of all of this, the limit as x approaches 2 for h, I could rewrite this using L'Hopital's rule, which says I can take the limit of the numerator, which is 2x, over the limit of the denominator, the derivative of the numerator over the derivative of the denominator. I'm going to use power rule here. This would be 3 times f of x, quantity squared, and then by the chain rule times f prime of x. Well, that has to equal 4 since h is continuous and thus differentiable. Remember, we mentioned that earlier. You can mention that again if you want. F of x and h of x are continuous and thus differentiable. Now, you have to mention that somewhere before or during part C. If you mention it before part C, they will read up. But if you mention it after part C, they will not read down to include this. So you can mention it before or during. Well, if I substitute in now a 2 for each of these, I can get an equation. So on that numerator, 4 is over 3 times f of 2, quantity squared, times f prime of 2 should equal 4 over 1. Well, that means the denominators have to be equal. So 3 times f of 2 quantity squared, well, we just found that f of 2 is 1, plus f prime of 2 would have to equal that denominator of 1. So then f prime of 2 should equal 1/3. Should equal 1/3. I'm just checking. I did that wrong. That's not plus. This is times. There we go. Equal 1/3. All right. Let's just check and see how we're doing on A, B, and C before we move on. Just in case I've caught an error, we should fix it. All right. Let's see. Oh, yeah, look, there's an error there. I must have written this wrong. It has a minus. Looks like it's got a minus that I missed when I rewrote this. So when I wrote this down, somehow I missed my minus sign. Oh yeah, it's 1 minus, so this has a minus right here that I missed. Okay, I was suspicious that something was wrong there. All right, let's just check A, B, and C so far though on the scoring guidelines for this. So for part A, we just have an answer. Okay, they didn't say you had to justify it, so just 1 point, we got that one. For part B, we need that product rule to be able to be seen, which we've got. Remember, that could be written in a different order. So just the fact that you use product rule, even if you don't use it perfectly, if you have the form of product rule, you'll get that point, even if you miss it partially, because sometimes kids just struggle a little bit on actually the mechanisms of this. But if you use the form of product rule, you get a point, and then if you use it correctly, you get a second point. So this was actually worth 2 points. And then the final answer, even if you did not simplify, is worth the 3rd point. All right, part C. Notice that they did state that the F is differentiable and thus continuous, and later on they'll say that for F. Okay, so we do need to make sure and mention that. Let's see, we've got that for part 1, they want us to recognize somewhere that limit equals 4. We did do that. F of 2 is equal to 1. We got that somewhere. Where did they put that? There we go. F of 2 is equal to 1. Okay, my notation was a little bit different, but we did talk about that equaling the limit somewhere. You've got to have that somewhere. We have that, and we did get that final answer. L'Hopital's rule. We used L'Hopital's rule to show that to do the derivatives here. Now, I did it incorrectly, so I wouldn't have gotten that point since I did it incorrectly, and I would not have gotten the answer point since I messed up and I missed my negative. So I would have only gotten 2 out of 4. The way we have it written now, we have 4 out of 4. So I'm going to put 4 out of 4 on the paper, but just so you know, I would not have gotten that right because of my careless error. Okay, so we got 1 out of 1 here. 2 out of 2 here. This is now 4 out of 4 with the way it's written, but I only got 2 out of 4. All right, part D. It is known that G is less than H or equal to H on the interval from 1 to 3. K is a function, some other function that is between these for that interval. We want to know if K is continuous at X is equal to 2. Well, the way that we show that something is continuous, okay, the way that we show continuity is we want the limit as X approaches 2 from both the right and the left to equal K of 2. This is our goal that we're reaching for, okay? All right, so on part D, let's maybe start with K of 2. Earlier, we were told that G of 2 and H of 2 is equal to 4. G of 2 is equal to 4, and H of 2 is equal to 4. And we are told in the given for part D that G of X is less than or equal to K of X, which is less than or equal to H of X. Well, that would mean, and that's on that interval from 1 to 3, so therefore G of 2 is less than or equal to K of 2 is less than or equal to H of 2, and those are both 4. So K of 2 must be less than or equal to 4 and greater than or equal to 4, so K of 2 has to equal 4. Okay, so my goal is to show that the limit of K would also have to equal 4. Well, because G and H are differentiable and thus continuous, which we had stated earlier, but if for some reason you could state that again if you want. So they are differentiable and then thus continuous. Then what I could know is that the limit as X approaches 2 of G of X has to equal 4, and that also has to equal the limit as X approaches 2 of H of X, because they're continuous, they have to equal G of 2 and H of 2, which both of those equal 4. Now, by the squeeze theorem, which you don't actually have to say the name of the theorem, but the theorem just says if a function's between 2 other functions, then it's squeezed between them basically, and its limit must be between their limits. So by the squeeze theorem, which you don't actually have to mention that name in order to get this next part, the limit as X approaches 2 of g of x is less than or equal to the limit as x approaches to, of h of x is less than or equal to the limit as x approaches to of, oops, this was k, alphabet soup here, of h of x. And so 4 is less than or equal to the limit as x approaches 2 of k of x, which is less than or equal to 4. Therefore, the limit as x approaches 2 of k of x is equal to 4. And notice that is also k of 2. Thus, k is continuous at x equals 2. Let's just check the answer. All right. Where is it? That's the wrong one. Oh, it's 1 point. 1 point for all that work. Okay, we have to say that they're differentiable and thus continuous. We did. We have to say that g of 2 and h of 2 equal 4, which we did. We have to say then that since k is between those, k of 2 is equal 4. And we also had to say that its limit was equal to 4. And since those are the same, therefore it's continuous. We did it. So we got 1 point for all of that. And we got our 9 points there. All right, that is the end of our video.